Appears to be working. Okay. So distance. Several distances that you need to be able to calculate. First, we'll go from a point to a plane. And to do that, if you remember pre-calculus a long time ago, there was a formula that was the distance from a point to a line. And if you do math team, you've probably seen this formula in some of the competitions. It was very similar to this. We're just going to add an extra letter, but essentially it's a times the x coordinate plus b times the y coordinate plus c times the z coordinate plus d all over the square root of a squared plus b squared plus c squared. So that's how you would find the distance. And of course, this is given a point x naught, y naught. Oh, thank you. And plane ax plus by plus cz plus d equals 0. So if they give you the plane equation and they give you a point, this is the formula that you would use to find the distance from that point to that plane. In pre-calc, oh, because I gave you a three-dimensional, yes. Thank you. Still stuck in 2 dimensions. Thank you. Oh, no problem. So, does this look familiar at all to you guys? Like if you remove the c squared and you remove this part, that's the point to a line formula? Some yes, some no. Well, if you forgot it, learn it now. It's fairly straightforward to use. Okay, and basically the idea to find the distance between, because we're also going to look for the distance from plane to plane and the distance from skew line to skew line. Okay, so we're going to reduce all of those scenarios basically to this one case where it's a point to a line. Okay, so even if it's more complicated, we're going to try to create point to a plane and then find that distance. Okay, so let's do the first basic example. So let's say we want to find the distance between point Q, which is at -154, and the plane 3x minus y plus 2z equals 6. And if you're a visual person, we have a point, right, and some plane. And what we're doing is finding that distance here. Okay? All right. So all we do is plug it into the formula. The only thing that we have to be careful with is this condition here. The plane equation must always be equal to 0. If it's not, you have to make that adjustment. Either write it out or just remember that here d would actually be -6. Does that make sense? And now we just plug everything in. So we do absolute value of a, which is 3, x coordinate -1, plus the b value, so -1 times the y coordinate, plus 2 times the z coordinate, plus the d value, so -6. And then that's all over the square root of a squared plus b squared plus c squared, so that'll be 9 plus 1 plus 4. What's the numerator simplify to? 6. And that's just going to be root 14. And that's good. So it's a pretty straightforward calculation. Any questions on how to use the formula? Okay. So the next example, let's do find the distance between parallel planes 3x minus y plus 2z equals 6, so same as before. And let's do 6x minus 2y plus 4z equals negative 4. Okay, so obviously these are parallel. We know that A because it told us, but what else could we look at in the equations to determine that these are parallel planes? Yeah. 3, negative 1, 2, 6, negative 2, 4, scalar multiples, right? If they share the same normal vector or a scalar multiple of the normal vectors, then they're parallel. Okay, so here's what we have. Parallel planes. We want to find this distance. What can we do? Yeah.
Since the distance between the two planes is going to be the same thing no matter what, just pick an x, y, z that satisfies one of the equations.
Sure.
Plug that point into the distance.
Very good. So let's pick a point. Hi. Pick a point on one plane. Any point, right? I'll just look at the first equation. And to make life easy, let's pick the easiest option. If I, well, I was thinking 0, 0, 3. Right? But you can do whatever point you want. So now, really it is finding the distance. So let's say 0, 0, 3 is over here. We find this distance. It's going to be the same exact distance as Brandon was saying. Okay, so the calculation after that is the same. Distance will be the absolute value of. So now we're going to plane number 2, right? So it'll be 6 times 0 minus 2 times 0 plus 4 times the z coordinate. What's the d value? 4 all over the square root of 36 plus 4 plus 16. So in the numerator, 0, 0, 12 and 4 is 16. And in the denominator we get root 56. I think that simplifies nicely. That's 2 root 14, so this is the same as 8 over root 14. Okay, any questions on that? We have one more problem to do. Yes?
So when you're picking a point on one plane,
Yes?
then you have to use the other plane for your vectors?
Absolutely. Otherwise, when you plug it into the first equation, you're going to get, and that's how you know. If you get 0 when you do the calculation, you just found the distance from the point to the plane that it's on. So make sure that you switch it up. Anything else? Okay. So the hardest case is skew lines. But again, we're trying to reduce it so that it's just a single point to a plane. If we can do that, then we know how to do it. So let's say we want to find the distance between skew lines L1 and L2. And let's say for L1 we have x equals 1 plus 4t, y equals 5 minus 4. I wrote 5, but I meant 4. Sorry. 5 minus 4t. And z equals negative 1 plus 5t. And for the second one, x equals 2 plus 8t, y equals 4 minus 3t, and z equals 5 plus t. Yeah. Okay. Yes.
I was thinking that since they're skew, there will be some point in which two of the coordinates are equal, a third one's different. So if you could find that point, then you have the point where the distance will be shortest because it's going to be like directly above it, and then you can just do point to line.
So how would you find that point? You're right.
Go
You have
with-
to take away one of the parametrics. So it'd be like looking at it from like a bird's eye view, and then it'll look like two intersecting lines. You know?
I do know what you're saying. Absolutely. I just don't. How do you find the coordinates then?
Well, yeah, solve it. It's like a system.
Okay. We've never done it that way, but let's do it and see what happens. So what would you?
Solve for t in one of them, and both of them plug it in and solve the system x and y.
Solve for t in one of them.
Yes, and then like
So
plug that
like
into
solve,
other
like
two.
for example, x minus 1 over 4, then plug that into the y equation.
Uh-huh.
T. So then you're gonna get like an x and a y.
Sure.
An x and a y.
How do you
and
know
solve
that
the
you
system.
picked the right one though?
If it works for another one of them, then you know you picked the right one. But if both of them give you
Different answers?
yeah, then you know that it's incorrect.
Okay. You want to do that and
Is
see
there
what
a more
happens?
efficient way?
Let's do it a different way. Yeah, let's not do it that way.
I actually really like that. It sounds like it's shorter.
Can we do it like the way you know how to do it
And then check it out that way? Okay, let's do it that way. Let's do it the way that is the traditional method, but I do like the way that you guys are thinking there. I think that could work. So let's check that out in a minute. If they're skew lines, then they lie on parallel planes, right? So I'm calling this plane 1 and plane 2. Yes. So we're trying to reduce, we have two planes currently. We don't want two planes, we want a point and a plane, right? Well, actually, I should back that up. We don't even have two planes yet. We just have the lines that are on those planes. So here's one line. We'll call this L1. And then somewhere below is another line. Skewed. So maybe L2. Yes?
Right. I was just trying to, so if we did it the other way and tried to find just where two coordinates are equal, that's assuming that the planes are like parallel to one of the axes. Because if it's tilted a little bit and two of the coordinates are equal, they would be offset a little bit, and that wouldn't be the shortest distance. Like if they're like
Ooh.
this, and then you go straight down, that wouldn't be the distance.
Okay. So they have to be exactly
Yeah.
this way, that way, or which way did I do? This way, that way. What's your, or this way?
Yeah.
I think I just did the two same directions, but I know what you're saying. Yes,
The planes have to be parallel?
they have to be for skew lines. Otherwise, they're going to intersect at some point.
Because like for that top plane, that front left corner.
Here?
If that came down a little bit, wouldn't the line still not intersect?
But then the
Then
bottom
you
plane would
have a
also
different
rotate.
plane.
The bottom plane would also rotate with it.
Why?
What's the definition of skew lines, you guys?
They lie on parallel planes.
There's not only one plane that you can align on P2 or L2. So
Oh,
if
okay.
plane 1
Yeah.
is turned a little bit, you can turn the second one.
Right. Man, you guys are, I like this, thinking way outside the box. This is good. This is going to be a good year.
Wait, but
or a very bad one. I don't know which one yet.
Leave that one like that. The lines won't intersect with that.
What's that?
If one is like this, one line, and then there's like that, they're still never gonna intersect.
No,
But
because
then-
now then the bottom
The
plane
plates will
relatively
intersect,
rotates
the
with
lines
the top.
won't.
But you can change
Hold
the
on.
way
Here's what
the
they're
bottom
saying.
plane-
If you rotate this plane a little bit, right, and you can still have skew lines, well, then you can rotate the bottom plane with it as well.
Why is
Some planes are parallel by definition.
Right.
What they're saying is that if they're skew, there is an alignment of two planes.
In fact,
that,
there is an infinite amount of planes that would contain L1 and L2 that would still keep them skew.
So for the purpose of the problem, we're trying to find.
I'm just drawing it this way so that we can see what the heck's going on. Do you really want me to draw it like this? And no, right? So I'm drawing them perfectly horizontal. They're not, but this is going to help us visualize the method. Okay? So we have two skew lines. If we had a point and a plane, that would be great. I don't have a point yet, and I don't have a plane. Okay? So first, let's pick a point, because we need a point. So I'm going to start on L1. So here's my point. Let's call it Q1, since we were using Q earlier. Now actually go ahead and do, after we discuss what we're going to do, I'll do it. So what's the easiest Q1 point to have here? Where T is 0, so Q1 would be what? Good. So now I have a point, right? Now I need a plane. Yes.
maybe take L2 that has a slope to it.
Mhm.
If you use that slope and that point Q1, you can make a line like point slope or whatever. It'll be parallel to L2.
So take the slope. You mean the vector 4, negative 4, 5?
Yeah, because like if you take L2 that has like an alignment, and if you take that Q1 and you make an alignment that's up here and parallel to it, you can make parallel planes from that. Does that work?
I'm not seeing it. It might. Let's finish what I have here, and then we can talk your other ideas. Okay? We have a point, we need a plane, right? Ideally, we want to use this plane, correct? So this is the plane that I want to use, because now I have a point. If I can find the equation of this plane, then we're good to go. Well, what two things do we need for the equation of a plane? Yeah, so we need a point on plane, or on L2, which, again, do the easiest one, which would be when t is 0. So we get what? Good. Two and 3 are going to give us the plane equation, right? So now we have the point that's on P2, because if it's on L2, it's on P2, right? Now we just need a normal vector. How do we find a normal vector for plane 2? You're close. What operation do we have with vectors that give us normal vectors? Cross product, right? So here's the argument. If I have a vector on L1, these are parallel planes, right? If I were to slide or translate this vector down to plane 2, and then take any other vector on L2, you guys see what I'm talking about? If I cross these two vectors, what do I get? I get a normal vector to both planes. Does that make sense? Well, I have a vector on plane 1 already, right? So what's the vector on plane 1? 4, -4, 5, right? The second vector from plane 2 is 8, -3, 1. So if we take the cross product of those two, that'll give me a normal vector to not only plane 2, but also plane 1, but we don't care about that. We just want the equation for plane 2. So let's calculate that. Explain.
Or can you just label V1 or V2 on the
Sure. So this would be V1, but then I went ahead and argued that I could slide V1 onto the second plane because it's parallel to it. So now I'm crossing V1 with V2. So if I take two vectors and no matter where they are on the plane, right? If I take the cross product, I'm going to get normal vector.
Wait, how can you just slide the vector down without changing anything?
Well, vectors, just like when you add or do anything with vectors, right? All that you care about is two different things for the vector, the magnitude and the direction. They can be positioned anywhere, right? So if these two planes are parallel, there has to exist a vector v1 on plane 2 that's the same one,
Okay.
right? And if you take this cross product with the vector that's on L2, then you get the blue normal vector.
I got you.
Does that make sense?
Yeah.
Yes.
So, how did you get V1?
V1 and V2 are just from the vectors that are on the lines themselves. Does that make sense? Okay. Anything else? Yes.
So this new vector you have, and
Well, I haven't gotten it yet, but yes.
or when you get it,
Yes.
is that gonna be like? Do we know that it's gonna stop right at the second plane, or?
It doesn't matter how long it is. All that we care about is that it's a normal vector. It could be short and it may not even reach that plane, but that vector can be, yeah, we need that. Yes, we need a normal vector and a point. As long as we have those, then we're good to go, and then from there we can reduce it back to a point to a plane, and then use the distance formula. Anybody have it yet? 11:36:20. Here, let me just set it up. Anyone else confirm that? I think that's what I have. Okay. So 11:36:20 is the normal vector. So now, from steps 2 and 3, we can write the equation for this second plane. Does that make sense? What would it be? We have a point, right? That's on the plane, and here's our normal vector, so we just plug everything in. It's 11 times x minus 2 plus 36 times y, where is it? Y minus 4 plus 20 times z minus 5 equals 0. So that's how we start. But if we're going to do the distance from Q1 to plane 2, Q1 is set up properly. Plane 2 is not in the proper format right now, so we have to multiply it out and move things around, right? So we'll have 11x, 36y, 20z. Now the constant, negative 22. You guys figure it out. Negative 100, negative 122, negative 144. or negative 266. Yeah? So now we are set up. So all this work, let me switch back to 4, blue, same blue color. Now find distance from what point? Q1 to
Oh, it's
the plane below it, plane 2. It has to be the same distance. Okay, so the last part of the calculation is D equals absolute value of, and again, we're using plane equation for plane 2 and Q1, which is all the way up here. Okay? So the distance will be what? Absolute value of 11 times 1 plus 36 times y coordinate, which is 5, plus 20 times z coordinate, which is negative 1 minus 266, all over the square root of 11 squared, 36 squared, and 20 squared, the sum of those. And I need your help. That's the answer. Oh, that's the denominator? So root 1817? What's the numerator? 95. Okay. Yep. So that is the end of the notes officially.